Hi everybody, this is Dr. Momin. This is our second presentation on PowerPoint for chapter 2. This is included in week number 2, and the topic for this presentation is logic, propositional logic. So I'm going to introduce in here the truth values and the truth tables for Boolean logic propositions. I'm going to introduce also the OR statement, the AND statement, the negation statement, the implication statement, and the if and only if statement. We refer to the proposition as the letters little b, little q, little r, and so on. But first, I'm going to introduce the what is considered a proposition. A proposition is a statement that could be true or false. It is a declarative sentence, and it has to be either true or false. A question cannot be true or false. An order cannot be true or false. So here is an example of a proposition or a statement that could be true or could be false. York University is in Toronto. That is a complete sentence, and it could be true, it could be false. York University is in downtown Toronto. All students at work are computer science majors. That could be a statement, could be true or false. So those are some examples of what we consider them. Another example we can say in a mathematical statement, 5 plus 6 equal to 11. This is a complete statement, and it could be true, it could be false. In this case, 5 plus 6 equal to 11 is a true statement. Here is an example of not a proposition. A question: do you like this class? Did you go to the movie? Please sit down. Please come early to the class. Do not move around. These are not a statement. This is an order, or it could be a question. Another example in here where we don't really know, it could be a true or could be false depending on the X. There are X students in this class. Well, I cannot tell you unless we know the value of X. So without knowing the value of X, we cannot say that this is a statement or a proposition because X is not known. Here are some more examples. A proposition could be a true, we refer to this one by the letter capital T, or a false by the letter capital F. In some other binary notations, we can use 1 for true and 0 for false. The moon is made of green cheese. This is a complete sentence. It is a proposition, but in this case, we know that it is a false statement. So the value for this, the truth value for this one is an if. Go to town. This is an imperative, so it is not a statement. What time is it? This is also is not a statement or is not a proposition. Propositional variables, we use the little p, little q, little r, little s, little t. New propositions from old. The calculus of propositions relate new propositions to old using. And we're going to use the truth tables. Now, a truth value is one value. A truth table is a table, as we can see in here. Variables b, q, and r and s are referred to the different statements, the simple statements. And then we look into the negations, which we use the letter tilde, means that not b, not q, not r, not s. So when we put tilde in front of the proposition b or q or r, then we negate that statement. The first table I introduce in here is the truth table for the negation. Now, what we start with the first column. B has two possible values, either true or false. So the truth value in here can be a true or a false, but the table itself has to have the two possible values for the P. Then we look into the negation, not B. Now, in this case, if B is true, then the negation will be false. If the original value is false, then the negation will be true. So we got to remember this. Now, the example in here is that we read it like that, not B, or it is not the case that B is true. Here's an example. B is a statement that it rained more than 20 inches yesterday. Now, that could be true or it could be false. The negation now is in the English language would be it did not rain more than 20 inches yesterday, or we can come and say it is not the case that it rained more than 20 inches yesterday. Another example in here, I am going to town. This is not B, I am not going to town. It is not the case that I am not going to town or I am not going to town. Now we introduce now two new truth tables. One for the conjunction, which is the and another one for the disjunction, which is the or. Now remember, conjunction is the and. So I wanted to Toronto and I wanted to New York. I am a good student and I am in VIU, and so on. Disjoint would be an or statement, or disjunction. We say I wanted to New York or I wanted to Toronto. I am a good student or I am under 5 years old, and so on. So here is when we construct the truth table, we put the first column B and we put 4 values because we have 2 variables in here, P and Q. So since B has 2 possible values, Q has 2 possible values, so the B and Q together will have a combination of 4 possible values. So we start with B and we put T and T and then F and F, and that's what I wanted you to do when you do your truth tables. When you construct your truth tables, you have to do it this way. And then we start with Q and we put true, false, true, false. So we have 4 possibilities in here, true and true, true and false, false and true, and false and false. Now let's look at the first column in here for the column for the conjunction, which is the and. B and Q, in this case, it will have true, false, false, false. So it is only true when if both of them are true. Now, it is false in the other 3 cases. When we have either B true or false and Q is false and true and false, all of these, if they are different, other than if they are different, or if both of them are false, then it is false. That's for the and. So it is only one true when both of them are true. Versus the or. B or Q, it is true if both of them are true, it is true if one of them is true, and it is false only when both of them are false. Now that is the true state for the and for the or. Here is an example. B, it is below freezing. Q, it is snowing. As a conjunction in here, which is and, we put the word and in between. So it is below freezing and it is snowing. Or it is below freezing but snowing, or but now snowing. So the word but and do the same effect on relating these 2 sentences. The disjunction is the or. We can come and say it is below freezing or it is snowing. or we can come and say it is either snowing or below freezing or both. Here is an example for conjunction, and we use that symbol for the and. So we say B and Q, I am going to town and it is going to rain. If B was, I am going to town, and Q, it is going to rain. Now that is the conjunction. The disjunction is the or statement. I am going to town, that's B. Q, it is going to rain. So B or Q, I am going to town or it is going to rain. Now the next truth table would be for the conditional. If then, and we use this arrow going from left to right, B then Q. We read it like this: if B then Q. The hypothesis is B. Q is the conclusion. The hypothesis is B, and Q is the conclusion. As an example, if you turn in a homework late, you will not be graded, or it will not be graded. If you get 100% in this course, you will get an A+. That is an if statement. So the hypothesis is in here. For instance, if you get 100% on this course, then you will get an A+. That is the conclusion. Now, when we construct the truth table in here, we see that the truth table will have the column if B then Q, the same constructions of the truth table. We put B with 2T and 2F, and then Q alternate TF, TF. And then we will put in here the only value in here which is false. If we start with true for B, then Q is false. And we come and say in here, for instance, for the promise, if you say, I promise you that if you get a 100% on the course, then you will get an A+. But suppose I didn't give you an A+, that is a false statement in here, so that is why we have F over here. So now remember, now it is true all the cases except when you start with T and the conclusion will be F. Now that is the new column in here. Now the another column in here I added is just because I wanted to show you that an equivalent statement that is the same as if B then Q is the negation of B or Q. The negation of the or statement B or Q. Now, if you remember the truth table for the B or Q, it is by itself when B or Q, when both of them are true, then we will say that the answer will be the same thing in here as it is true, false, true, true. Let me move on to the definition of if B then Q. This applies to the fact that we can come and say if B then Q. That's what the original statement. Another meaning in here is that B implies Q. If B, comma Q. B only if Q. B is a sufficient condition for Q. Q if B. Q whenever B. Q is a necessarily condition for B. So all of this is the same meaning for the implication if B then Q. Now, as I mentioned before, the implication is false if when B is true, Q is false, as we saw that in the truth table for the implication if B then Q. Here are some examples. if the moon is made of green cheese, now remember this is a false statement, then I have more money than Bill Gates. Well, now this second statement Q in here could be true, could be false, but it doesn't matter since you started with an if. We knew from the truth table that we had before that if we start with an if over here, regardless of whatever the value of Q is, the truth table will be always true. So whenever you start with a false statement, it doesn't matter what is the conclusion is, true or false, you always have the true value. Another example in here, if 1 plus 1 equal to a 3, which is a false statement, then your grandma wears combat boots. Well, that could be true, could be false, it doesn't matter, but the conclusion is true. The implication in here we started with the hypothesis is false, so the complete answer for this is true. And some other examples. Now, the logical equivalence of B then Q and not B or Q are logically equivalent. We can prove that by constructing the truth table for not B or Q, and for the truth table for B then Q, and we'll find that they have the same truth columns in the truth table. That is a way to prove that some compound statement is equivalent to another compound statement. Now, before we move on to something else, we will still deal with the if B then Q. What would be the contrapositive? We define something called the contrapositive of the conditional statement B then Q. The contrapositive would be not Q then not B. Not Q, A then not B. That is the contrapositive of the statement, of the conditional statement if B then Q. The contrapositive is always has the same value as if the conditional statement. So it is they are equivalent in if we construct a truth table for that. So both of them have the same value. The contrapositive of if you get 100% in this course, you will get an A+. That is the conditional statement. Now the contrapositive, which is not Q then not B. Not Q means if you do not get an A+ in this course, this means that you did not get 100% on the course. That is the contrapositive. Now, another thing in here we included is that is we can prove this one using the contrapositive, using the contrapositive in here that we say if x squared is even, then x is even. All right. Now the proof for this one, x squared equal to, let's assume that x squared equal to 2a because it is an even. For any a, 2a is an even number. Since 2 is a prime, 2 must divide x. Now the proof number 2, if x is not even, then x is odd. Therefore x squared has to be an odd because the square of an odd number is always an odd number. This is the contrapositive of the original assertion. The converse in here is of the conditional statement, which doesn't have the same value as the original statement. Now it is not equivalent in terms of the conditional. The converse is of the B then Q is Q then B. All right. Now you can see in here that they are not equivalent. If we take this example in here, if you get 100% on this course, you will get an A+. Versus now the Q then B, if you get an A+ in this course, you scored 100%. These are not equivalent. These are we don't guarantee that. Here are some examples in here in order to do the contrapositive. we identify them and we convert them using this one in here. So if we give you a compound statement like this, we say B, it is raining tomorrow. Q, it will not go to, I will not go to town. The symbol in here for the conditional statement, if R is the statement equivalent to if B then Q. Symbolize the converse now, Q then B. Convert the symbols back into words. If I don't go to town, then I will it will rain tomorrow. Or raining tomorrow is a necessary condition for my not going to town, or my not going to town is a sufficient condition for it is raining tomorrow. The last statement I'm including in here, which is the if and only if. It is a biconditional, and we say if B, if and only if Q. Now the truth table for this is always true when both of them are true, or both of them are false, and it is false otherwise. So the truth table for the biconditional statement, as we have seen it before in here, if you start with if B then Q, then you will have true, false, true, true. If you go the other way around and you start with Q then B, then you will have true, true, false, true. And so the answer for the biconditional is true, false, false, true for the truth table for the if and only if. I'm going to stop over here, and I would like you again to try to do the odd number problem from section 1 and 2 of chapter 2, excuse me, in chapter 2, the logic, and check your answer with the answer given at the end of the book. And I encourage you to do all of the possible values, possible problems of odd numbers, and compare your answer to the answers in there. If you don't match them and you can't figure out your mistake, then email me, and good luck to you guys with chapter 2.